Okay, students. Let's get ready with the lecture. I want to take attendance. So turn on your clicker and just click in a letter. Just vote, any letter. Doesn't matter, I'm just taking attendance with this question. Okay, that's fine, thank you. We're going to have a clicker question in a minute. That was just taking attendance. Let me get these are my this is my backup microphone system, just my earbuds. Let me bring this volume down a little bit. All right. This is the last lecture of the semester, and let's make it a good one. We're going to finish up talking actually a little bit about Galileo and his whole idea of looking at the universe, gazing at this book that we call the physical universe. And we're going to bring it all together. But before we do that, let me just point out that for us, the final exam is Thursday, December 6th. It's a week from today, 7 a.m. to 9:50. And please make a note, if you are tardy, you're going to be in deep trouble. If you come in after the first person finishes, the students that are on time, and the first person's going to finish in about 30 minutes, and you come in here at 7:45, you're toast. You can't take the final. All right? Okay, that's the rule, and that's the rule with midterms. It's also the rule with the final, and I've done it on finals, and I've done it a couple times this semester on midterms as well. Students coming in late. All right. Also, you may not take the exam with the other section. If you do, it'll go in as a 0. All right. You have to be here at this time only for this time, and you have to be on time. Okay. And so that's the rules. Any questions about that? Final exam procedure. Okay, a couple of words about homework. There are 2 homeworks running inside web courses, and they're going to activate or become available to you at, I think, 2:30 this afternoon. Okay, one of them is a regular homework assignment related to the stuff that we talk about today for the first hour. And then the other assignment is the big mega review assignment, and that's going to be converted into bonus points. If you look at the homework page, you'll see that they're both posted there since last night. And I may fool around with them a little bit, but 2:30 should be good to start that. Okay, and that'll be due. I think both of them are set to be due at 6:59 a.m. on December for this section. 6:59 a.m. So in other words, right before the final, just like regular homework assignments. Okay, questions about that? Okay, let's keep going. Last time we were talking about diffraction and the spectrum of hydrogen, and we talked about the spectrum of helium and the spectrum of neon. And we noticed that the colors were different. And those are like the fingerprints, what we would call the spectral or the quantum fingerprints of hydrogen and helium and neon. And any element that you can isolate chemically and then try to make a gas out of it, vaporize it, and then look at the spectrum, you can frequently get a visible or an ultraviolet or an infrared spectrum. Now, we were looking at visible. Axel.
How does the final exam can be structured? Does it have the two questions?
You're a little late with questions about the final. It's going to be like a midterm except twice as big, and it's going to be comprehensive. So it'll be both sides of the scantron, a bunch of, just it's 100 points instead of 50. All right, so you'll have some clicking. You'll have some scantrons, so you might have 90 scantron dots or 82 or something. I haven't written the final yet, but come to the final and you'll find out. All right. All right. Now, anyways, so now one of the things that I mentioned to you is that when you're looking through the diffraction grating, you actually see what we call the central image. It looks like the naked eye image. That's this one right here. And for us, it kind of had a pinkish hue to it, which is a combination of all the other colors of hydrogen. Like when you see the sun, you see all the colors through your eye at the same time, and they look white. Sunlight looks white. But when you break it up in a prism, it breaks up into all the different colors, Roy G. Biv. So this is the central image. It's considered a diffracted image, but it's the central image, so all the colors come back together. They go straight through and they just, hit your retina without having done significant diffraction. Now over here, you'll see in this picture, and this is actually a picture from the lecture hall in the physics building. H gamma, one of the purpley lines, I think many of you saw. H beta, the kind of aqua line that many of you saw. And out of the picture, beautiful red H alpha, also distinctive. And, so an astronomer sees these, he looks at a star and he puts the starlight through diffraction grating, and then he has a real precise photometer, like on the Hubble Space Telescope, ultra precise. And they can measure individual wavelengths like this. And if they see these ones are bright and nothing else, then they know, a lot of hydrogen. If they see that these ones are bright and then maybe a few from helium that are also bright, a lot of hydrogen and a lot of helium. So now here's the diffraction grating that we looked at. And I want to show you just how this will work in a laboratory. And see, this student is holding it on the edge without putting their greasy fingerprints on it, which is good. And this is kind of what yours looked like. Did anybody make a note of how many lines per millimeter on your diffraction grating? Because they're not all the same. Did it? Was it 500? Okay. So 500, can you imagine that? 500 per millimeter? That's 500 times 1,000, 500,000 per meter, which is about this long. So they're very close together. Here's kind of a schematic of what they look like. All right. And this is, blown up. I mean, they're not this far apart, but you can think of them as being something like that. Here's a face-on view of it. When the light comes through the diffraction grating, here's what happens. See if you can make a sketch of this. And this is just for a pure red source, but hydrogen lamp is going to be a source of H alpha red plus some H beta aqua plus a couple purpley H gammas and H deltas. But this is just doing the red. And there's a certain specific angle, theta, down here. And at that angle, theta, you'll see the red H alpha line. You know, over here, down through the center, over here, where my cursor is, you'll see the central image. Okay, and that's all the colors together. But over here, dipped over to the right, you know, here's your eyeball up here. Okay, you are here. Okay, so, you know, you're looking at this, and this is dipped over to the right slightly. All right? And then the blues and the purples are also dipped over there, but this is just a diagram for the red. So there's a precise angle. And the reason for that angle is because wave number 8 up here, to get to your eyeball up here, wave number 8 has the longest path. All right, and wave number 1 has the shortest path. All right, because your eyeball's up here, so number 1's going to get there a little bit faster. All right, the angle is determined by the wavelength of the light. Path number 7, when path number 7 and path number 8 are at the right angle, then path number 7 will be 1 wavelength exactly shorter. And that means that everywhere along that angle, you'll have constructive interference. It'll be brighter. Wave number 6, that's the next one. That's this one here. This is the third arrow from the bottom. That'll be 2 wavelengths ahead. All right, 2 wavelengths is nice. Now, if it was half a wavelength or 2.5 wavelengths, you'd get destructive interference, and that's what happens at a different angle. You know, only very specific angles will you get constructive interference. All right, but only this one for H alpha. Now here, let me let you get another. So here's the diffraction grating here. All right, and we've got here are the lines. This little black line here, you're seeing the edge of it. All right, and it looks like, you know, we're looking down on it along the edge of it. But if we were over here, it would look like, you know, an old-fashioned jailhouse door right here. Right, so those are the lines, and we're looking at them face on in this view, but over here we're looking at them in the overhead view. So each of these, so it looks like dashes here. Those represent the lines. And the wavelets form between each dash, and they form, you know, new wave fronts. And in this particular direction, you get constructive interference. So that's where you see the first H alpha. Now you'd see another H alpha down here dipped off to the left. And many of you saw that. You saw some reds off to the left and some reds off to the right when you were looking at it yesterday. Same thing with the incandescent light source. You saw rainbows left and rainbows right. All right, same thing here. This is just one color. Now here's a close-up. This is what's actually happening. When I say that there's a full wavelength difference, here's a kind of here are the openings right up here. Here's another one. The distance between the openings, you know, you get that from, you know, 500 lines per millimeter. They design the spacing at the manufacturing plant where they make them. Okay, so this is a known quantity here, D, and these dashed lines off to the upper right, that's these blue lines. So this is like H beta, and it's dipping down to the left here. And this line segment right here, all right, that bluish line segment, that's the difference in the path length. So for this top ray here, in this direction, it's going to be exactly 1 wavelength behind this guy right here. And 2 wavelengths behind this guy right here. 3 wavelengths behind this one, and 4 wavelengths behind this last one. Okay, but only at that angle. And that's this angle theta. All right? So this, if you could be shrunken down to the size of an electron microscope, or if we could look at an electron microscope and see these lines and stuff, it'd look, from above, it'd look something like this. All right, so that line segment there is the one that counts. Now, let me blow it up. Here's the line segment that we were just looking at, all right? And that's 1 lambda there, and this tiny blue triangle is a right triangle. And the hypotenuse of this right triangle is set at the manufacturer. So many lines per millimeter. Okay, so you know that. You know the hypotenuse, and you know the angle, and so you can figure out using trig, proportional triangles, all this stuff. Now, let's take a look at a blow up. All right, now oh boy, this is all blooped up. Let's go to the next slide here. All right. Now, in the lab, this is the actual triangle that you can measure. Okay, so you can measure this, so many centimeters here on this vertical segment, so many centimeters for capital D, and then you can use Pythagorean theorem for this long hypotenuse. And the point being that this triangle in the lab that you can see and you can measure easily because it's in the lab, so your distance, so here's your central image here, y subscript c, and y subscript m, that's your first constructive interference, that's your, your spectral line up there. That's the same as that tiny rectangle that we were just looking at. All right? So the geometry of both of those are the same. Because those two triangles are proportional, you can figure out the wavelength. This bottom segment down here, this tiny segment in red down here in this view, that's 1 lambda. That's lambda. All right? And you can't see it, but if you can do the trig for this triangle and then say, all right, this is the same shape, and I know the hypotenuse of this one, ding, you got everything else on that blue tiny triangle. So we can get lambda. We can measure it in the lab, and it's not hard. Just a bunch of Pythagorean theorem and a little bit of trig or proportional triangles. Now, you can calculate lambda. Now, let me ask you a clicker question about wavelengths and frequency. So turn on your clicker. Because I don't want you to get caught napping on this. All right, so your first clicker question for today, and we're going to do a bunch of them, is simply this. If you measure the wavelength in the lab, can you get the frequency? Which formula can you use to get the frequency? Go ahead and vote. Wave equation, impulse equation, latent heat formula, or Newton's second law. And hey, you guys, you know what? This would count as a formula matching question, although it's in the form of a concept question. But it would be a way of giving you a bunch of formulas on the midterm outside of the matching. Hey, wait a minute now. Who are you? Yeah. What? And you're a student in this class? But you don't always sit next to Casey? Okay. Okay. So I just was checking because you look almost like twins. So I thought, like a Twins Day at UCF, which, sometimes people, they finish the semester earlier than at their own college and stuff. All right. So you're good. You're good. Good. Mackenzie, good. All right. So 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, and 98% of you got that one correct. Yeah, use the wave equation. If you know lambda, and we know the speed of light, then you can figure out frequency. Now, the reason that the frequency is important is because that helps us figure out atomic energy levels. Here's the formula. And Einstein is the one that kind of started the ball rolling in 1905. He said, look, if you have a photon, its energy is determined by this equation. Multiply the frequency by Planck's constant. And it works out perfectly. And so, Danielle, what the upshot of this is that if you can measure lambda in the laboratory, using a diffraction grating, you can figure out frequency. And call it, if you can figure out frequency, you can figure out photon energy. And the photon energy is the difference in the electrical potential energy of the different energy levels of the atom. All right, so now the EPE, as you know, for the hydrogen, this is for hydrogen. K times E squared over R. All right, and you've got to know R. So if you can figure out EPE over here, then you still don't know what R is over here. All right? And the photon energy is the delta EPE, the change when you jump down, when you make a quantum leap downward, the change in the potential energy. So it is determined basically by the color of the photon. A photon is low energy if it's red, and if it's violet, it's higher energy. Ultraviolet, even higher energy. Infrared photon, even lower than a red H alpha photon. All right. Now, the guy that figured how to hack this apart was Niels Bohr, and the other guy in that photograph. And he said, look, if you quantize the orbital angular momentum, then you can figure out the distance r. You can get an expression for that. And so then you're able to figure out everything about the atom. So you got, and for hydrogen, when he said this, that the orbital angular, and we studied this, MVR, easy. And Bohr was thinking circular orbits, all right? And as a side note, I'll just mention circular orbit, periodic motion, phase diagram, phase portrait, elliptical. And so what Bohr was saying is that the phase portrait comes in units of Planck's constant, h. So some number n, 1, 2, 3, 4. And Planck said, Niels Bohr said, that n equals 1 is the lowest energy state, n equals 2 is the second or first excited state, n equals 3 is the second excited state or the third energy level, and on up. And remember what Balmer's formula told us last time, that n equals 3 corresponds to H alpha. All right, so let's take a look at this. So Bohr said, all right, every one of these circles, the orbital angular momentum, MVR, is some multiple of Planck's constant. All right, so you have these certain altitudes. So knowing the nucleus, the charge in the nucleus, and the charge on the electron, and then saying it's got to be some multiple of Planck's constant, that locks in very specific orbital sizes, very specific altitudes. Now, at the time, Bohr just said, I'm just going to make this my rule, that the angular momentum has to come in bindles of Planck's constant h. He didn't know why that was, but we're going to talk about why it's true. So here are the energy levels. N equals 1. And he said, you know, the MVR, orbital angular momentum for n equals 1 is h. And for n equals 2, it's equal to 2h. And once you know that, you know r, and you can get everything else. You know, k e squared over r, and so on and so forth. All right, so you have countable energy levels, and you can figure out the dip in the potential energy from one level to the next. So here's a picture of H alpha. H alpha dips in Planck's and Einstein's theory. It dips from n equals 3, dips down, and makes a quantum leap down to n equals 2. And as it does that, it loses electrical potential energy. It goes into 2h orbital angular momentum, and it emits a photon. So here's your quantum leap. All right? You can't leap halfway between or 0.44 times the distance between those orbits, only from n equals 1 or n equals 2. All right? N equals 2, and you know, if you get a burst of energy in, if it's the right size energy, you can go from 2 up to 3. Okay? And the reverse process holds. So the red H alpha photon is emitted with the missing energy. And Planck's Bohr's theory about angular momentum, orbital angular momentum, it was perfect. It worked out exactly right, because they knew what the energy levels had to be. I mean, you could do a bunch of algebra and stuff and figure out the energy levels, but nobody knew why that was the case. But Bohr said, look, orbital angular momentum, some whole number times Planck's constant h, right on the money. Okay, so he was able to figure out the theory of it. But why does nature insist on orbits that only come in bindles of orbital angular momentum, some whole number times Planck's constant? Why is that? Why does nature insist on that? Because, gravitationally, we can, in gravity, the space shuttle, spacecraft, a satellite, rocket, anything, we can get to any altitude we want. But in the atom, apparently, the answer is no, you can't do that. All right, now the guy that figured that out is named Louis DeBroglie. He's a French guy. This is about 1925, 26 in there. And he said, look, you got this nice rule, Professor Bohr, up there in Denmark. MVR, orbital angular momentum, equals some number times h. It's lovely. But why is that? Well, his theory was, what if you treat the electron as a wave? He said, look, we've been thinking about electrons since the time of J.J. Thomson as a particle. But if you consider the electron to be a wave also, you can't go around saying that it's not a particle. But if you also say that it behaves as a wave, here's what you get. DeBroglie said, look, these orbits are chosen so that you get perfect standing waves going around in a circle for n equals 1, n equals 2, n equals 3, and on up. In other words, the electron is interfering with itself. Let me repeat that. In DeBroglie's theory, the electron behaves as a wave with a wavelength that fits exactly inside of its orbit. Now that means that its orbit can only have a certain size. And that is why orbital sizes are quantized. Because you can't, just like when we were up here with the coil spring, I couldn't use any old frequency to get a standing wave. I had to get it just right, and then I'd get the fundamental, or the first excited state, or the second excited state. Only certain frequencies, and that was from left to right. And the same thing holds if you're going in a circle. Only certain wavelengths will fit. And that's what Louis DeBroglie said. It'll be constructively interfering with itself. Just as our wave up here on the stage, was constructively interfering with itself. I was sending out a set of waves, and they were reflecting off the student and coming right back. Okay? Now, we also know that this is true, for instance, on guitars. And, so if you set the length of a guitar string, and actually if you also set the weight of the guitar string, so a big string versus a little tiny string, you'll set the frequencies that string generates when you strum it. And if you use the fingerboard, you change the length. And it changes the note that you produce from that string. And you put a bunch of them together, you get a beautiful chord. All right, so we know that on guitar, a couple years ago I had a student that was really good at guitar. She just came in and showed all kinds of different chords and stuff. And the atom is just like that. It's like a quantum guitar. Once you have the nucleus set, one proton, then all the guitar strings are set. And you get very specific frequencies and wavelengths. And this is a picture of the wavelengths. Now, how do you actually calculate it? Here's what DeBroglie said. You use this formula, lambda equals Planck's constant divided by the momentum. H over mv. So the momentum controls the size of the wavelength, and that's exactly what we know about orbital energies and stuff. It all fits together. It's all consistent. So this is called the DeBroglie relation. Lambda equals h over mv, or h over p for momentum. Either way. By the way, Mackenzie, you're not in trouble. I don't want you to, There's not a single person in this lecture hall right now that's ever been in trouble with me. I'm just looking around here. I don't see anybody that I've ever felt like they were in trouble with me. So I don't call on people to, I call them just to learn names and stuff. Right, Casey? You're one of the first person's names I learned. Question? No, if you came late for that question. But we're going to have the bonus clicking in a few minutes. So if you hold on for that, you'll be able to get a bunch of bonus points. And that'll cover, one clicker question today isn't going to kill your grade. It might not even change it. If you have 25 out of 25 now, you probably still have 25 out of 25. So one clicker question won't change it by much. So here's what we got. DeBroglie says, let the wavelength lambda be calculated from the Coulomb interaction and electron momentum using Planck's radiation constant h. Lambda equals h over mv. And so the Coulomb interaction, the size of the nucleus, the charge in the nucleus, controls the size of everything. So H alpha, H beta, H gamma, H delta, they're all controlled in that way by ensuring that the wavelength fits. So Bohr's insight was really, he didn't realize it at the time, but he was stating the conditions for the electron wave to be the perfect size where you get a nice standing wave. Only certain orbital sizes will permit standing waves for hydrogen. And if you go to helium, it's going to be a different set of orbital sizes because it's a different nucleus. All right? So, So n equals 2, that's this picture, the second set of waves. That's like the first excited state on our coil spring. You know, one frequency, one wavelength. It's higher than the ground state. The ground state is like the fundamental mode when we were doing that. And if you want to look at fundamental mode and first and second excited states, you can review the YouTube, the demonstrations videos in YouTube. So that's this picture. And you know, there's all kinds of pictures, but I like this picture a lot. Now, if an electron is a particle, how can it also be a wave? In other words, all right, DeBroglie's theory was pretty good for the hydrogen atom, but can you get an electron that's not bound to, for instance, diffract? Because particles won't diffract. So if you take a stream of electrons not attached to a hydrogen atom, will they diffract through us? For instance, will they diffract through a crystal? A crystal is the right size. And there's gaps. Question in the back? No? All right. Crystals have gaps, you know, very specific size gaps. So it's possible, you know, okay, let's zip some electrons through a crystal and see what happens. Well, that's what these guys did, Davisson and Germer. They observed it just a year or so after DeBroglie wrote down his hypothesis. And they found that the answer to this is yes, here's what it looks like. And this is a modern day image. This is nickel, I believe. And here's the reference to it. Passivity and electrocatalysis of nanostructured nickel encapsulated in carbon. So these guys are trying to figure out all kinds of carbon nanotubes and stuff like that. So this is from 2011. That is what electron diffraction looks like. They found it back in 1927. And so they proved that DeBroglie was right. And I can't overemphasize this. To say that an electron is a particle and a wave at the same time is like saying that you have a bookcase that is also a horse. You know, nobody would go around thinking that, but that's what electrons do. And they don't even think about it. That's just the way they are. It's a whole different kind of, when you're at that size and energy level, all those factors are very apparent. Now you are a system of particles bound together by your anatomy, and you do not display diffraction because you're so large, and we're going to show you why that's the case. And here's some more electron diffraction patterns. You know, at the right energy and wavelength, you know, you can get a whole set of analysis. You can figure out the shape of you know, you know, whether it's a cube, hexagonal crystal, dodecahedron, you know, whatever kind of crystal you have, you can figure it out using electron diffraction. And you can use X-ray diffraction for that as well. X-ray, of course, X-ray is electromagnetic radiation. So that's photons diffracting, but electrons do it as well. Now, I want to show you a calculation here of the wavelength of a macroscopic object. This is a paperclip. Now, the notional mass of a paperclip is 1 gram. Okay? And so what we're going to do is say, all right, we have a paperclip. Go ahead and write this down, because you're going to need to do this kind of a calculation in your homework. Paperclip has a momentum. Let's just say it has 2.65 times 10 to the minus 3 kilogram meter per second. All right, so that means that it's traveling at 2.65 meters per second. Now that's somebody walking across campus at kind of a, you know, kind of a slow pace. So, you know, getting a paperclip to move at that speed, yeah, do that anytime. So what we're going to do is use the momentum and Planck's constant. And there's the value for Planck's constant. Now, this is joule seconds. And, You can also use electron volt seconds for Planck's constant. But since this is a macroscopic object measured in grams and kilograms, we'll use this version. So we're going to put that in the numerator, and then we're going to put the momentum in the denominator, and then we're going to figure out what the wavelength is. All right, so here we go. So here's Planck's constant on the numerator, mv or momentum in the denominator. And here are the values, 6.63 times 10 to the minus 34. Now notice that I changed, Austin, the, excuse me, my headset just leaked up here. Notice that I've changed the units of Planck's constant from joules second to kilogram meter squared per second. And why am I doing that? Because my denominator is regular momentum, kilogram meter per second. And so, Michelle, I'm going to have a lot of canceling to do. And if you look at this carefully, kilograms cancel top and bottom. One factor of meters cancels from the top, one from the bottom. And then per seconds cancel top and bottom. So all you're left with is meters, which is good. I'm trying to figure out a wavelength. It better come out in meters. All right, so 6.63, 2.65, and I've combined my 10 to the minus 3 in the denominator, Tiffany, with the 10 to the minus 34 up top. So 10 to the minus 3 downstairs is like 10 to the regular 3 upstairs. And so I have 10 to the minus 31. All right, so this is going to be about 2 point something times 10 to the minus 31. Go ahead and calculate that. Anybody have an answer on that yet? You're going to need to do, for your homework, you're going to have to work really carefully in scientific notation. So the numerator is going to be about 2 point something times the denominator. So you're going to come out of 2 point something, I think. 2.5? Anybody else got a 2.5? Yeah, okay. All right, 2 point. Now, here's why we did this. For a paper clip, 2.5 times 10 to the minus 31 is a very, very small wavelength. Whoops. Whoops. Okay, it's really, really small. 10 to the minus 31 is many powers of 10 smaller than a nucleus. And because that is true, your weight, and this is for something that's a gram. Now you're measured in kilograms, so your wavelength, as your individual personal wavelength, is going to be even smaller than this. So when you go through a doorway, you're not going to see diffraction effects. You're just going to buzz right through like a particle, like a beam. Okay, you're not going to fringe out to the left and right the way we saw with the hydrogen, you know. So paper clip, a few miles an hour, 2.5 times 10 to the minus 31. It's many times smaller than any, you know, like your pocket where you might have a paper clip. So, you know, when you pull it out of your pocket, you're not going to see any diffraction. And that is why humans and apples, baseballs, basketballs, spacecraft, they don't show wave effects. I mean, theoretically, yes, they're waves. Collections of waves added together, but they're so small, the wavelength is so small because the momentum is so large. But atoms, nope. Atoms, very easy to see wave effects. Electrons, protons, neutrons also. We model neutrons that way. Now, we've got atoms, and each atom of hydrogen is like a quantum guitar. Now, look at this periodic table. This periodic table, look at it. Look at it. Look at the periodic table when it's talking to you. Every single, an element is an atom with a unique number of protons in it. So every atom that has only one proton is hydrogen. Every atom that has only two protons is helium. Every atom, now going down to the second row, every atom that has only three protons in the nucleus is lithium. So K times E squared is good for hydrogen, but for lithium it's K times 3E times K times 3E squared. And that changes all the energies. It changes all the energies, and so all the wavelengths are going to be changed. Energies, frequencies, everything is going to change. Element by element. Let me repeat that so you can write it in your notes. The periodic table. The energies, the colors of the spectra, the wavelengths that you measure in the lab, they're all, now you may have some accidental matchups, but you're not going to have anything exactly matching hydrogen. Everything on this periodic table is different than hydrogen. And everything is different from helium. Every cell other than helium is different than helium. So, if you think about it, every element in this periodic table is like a quantum guitar of a different size. And here's a picture of Chet Atkins, one of the best guitarists of the last century. Really good. Every element in there is like a different instrument in an orchestra. So Galileo's vision, the universe, he thought, the language is mathematical. And he's right about that. But when you look at the periodic table and you think of all the different frequencies and wavelengths, all the different nuclei, each element is like a different instrument in an orchestra of 100 and something different instruments. What that means is that when you look out at this book that we call the universe, you're really looking at a symphony of all the elements. Everything that you're seeing is because of that. All right. That concludes my lecture for today. But we're not done. There's still more.